Deep learning has taken the world by storm, powering everything from voice assistants in our homes to self-driving cars on our streets. But with a plethora of models out there, it can be a bit overwhelming to differentiate between them and understand their unique strengths and applications. Let's embark on a conversational exploration of the main types of deep learning models, making sense of the technology that's revolutionizing industries around the globe. First off, let's talk about artificial neural networks, ANNs. These are the foundational blocks of deep learning, inspired by the way the human brain processes information. ANNs consist of layers of interconnected nodes, or neurons, that process and transmit signals. When data is inputted, these networks work through many layers to eventually yield an output, learning from the data it processes along the way. Think of ANNs as the jack of all trades in the deep learning world. They can handle a wide variety of tasks, from recognizing handwritten digits to predicting stock market trends. Moving on from the basic architecture, convolutional neural networks, CNNs, deserve a spotlight. If you've ever wondered how your phone knows whether to tag a photo as containing a cat or a dog, CNNs likely played a role. They're specifically designed for processing grid-like data, such as images. By utilizing convolutional layers, CNNs can detect and understand spatial hierarchies in data, edges, shapes, and then objects. This ability to automatically recognize complex patterns makes them invaluable for image recognition and computer vision tasks. Then we have recurrent neural networks, RNNs, which are like the storytellers of deep learning models. Unlike CNNs, RNNs excel in processing sequences of data by having loops that allow information to persist. They're the go-to model for tasks that involve sequential data, such as time series analysis and natural language processing. The ability to remember previous inputs makes RNNs adept at tasks like language translation or speech recognition. However, it's worth mentioning that they struggle with long-term dependencies, which is where their successors, long short-term memory networks, LSTMs, come into play. LSTMs are a special kind of RNN designed to better handle long-range dependencies. They're particularly useful in applications where context from earlier data is crucial to understanding current input. Think of tasks like writing an entire paragraph or composing music. LSTMs help preserve important information over longer sequences, ensuring the model maintains coherence and context. For those interested in translation, summarization, and other language tasks, transformers have become the model of choice. Transformers have revolutionized natural language processing with their self-attention mechanisms, allowing them to weigh the importance of different words in a sentence relative to each other. This innovation underpins models like BERT and GPT, which can understand and generate human-like text with astonishing accuracy. What's particularly notable about transformers is their efficiency in parallel processing, making them capable of training on massive datasets faster than traditional RNNs. Beyond these, there are Generative Adversarial Networks, GANs, which are like the artists of the deep learning world. GANs consist of two parts: a generator that creates data samples and a discriminator that evaluates them. Through this adversarial process, GANs become incredibly proficient at producing realistic data, whether it's generating lifelike images, simulating environments, or even crafting music. They're a testament to the creative potential of deep learning, pushing the boundaries of what machines can generate autonomously. Deep belief networks, DBNs, are another intriguing model, representing a layered, probabilistic framework. They consist of multiple layers of latent variables and are particularly useful for feature extraction and dimensionality reduction. While less commonly used than some of the other models mentioned, DBNs illustrate the rich diversity of approaches within deep learning, especially in unsupervised learning contexts. Lastly, there are autoencoders, often employed as a data compression tool. They work by encoding the input data into a reduced dimensional representation and attempting to reconstruct it. While the concept seems simple, autoencoders play a critical role in anomaly detection, feature learning, and even data denoising. Imagine trying to distill a complex image down to its essence and then trying to recreate it. That's what autoencoders strive to do. Each of these models brings something unique to the table, catering to different types of data and tasks. The exciting thing about deep learning is how researchers and practitioners continuously hybridize these approaches, innovating new architectures to solve ever more complex problems. Understanding these various models not only helps in harnessing their power but also illustrates the incredible versatility and potential of deep learning as a transformative technology in our daily lives. Whether you're an enthusiast watching from the sidelines or a professional diving deep into the arenas of AI, appreciating these different models is key to grasping the future of intelligent machines.